Welcome to this introduction to Chemvue software, Pasco's dedicated application for students in the college chemistry lab. In this video, I'll demonstrate the key features of Chemvue for general data collection and analysis with Pasco sensors. To follow along, gather this equipment: a computing device with Chemvue software, a wireless conductivity sensor, 2 beakers, each with 100 milliliters of distilled water, 0.01 moles of sodium chloride, 0.01 moles of calcium chloride, a rinse bottle and paper towel, and, optionally, a stir plate and stir bars. I'll start by launching the Chemvue application. I'm on a Windows computer, but Chemvue is also available for Mac, iPhone, iPad, Android phones and tablets, and Pasco data loggers. Chemvue supports Pasco chemistry sensors and instruments, both wired and wireless. Connect a wired sensor, interface, or device via USB, and Chemvue will detect it automatically. To connect a Bluetooth low-energy device like this wireless conductivity sensor, power on the sensor, select the Bluetooth icon in Chemvue to open the wireless devices screen, and click on your sensor to connect it. Chemvue's live data page updates to show the primary measurement from the connected sensor or sensors. The default measurement for the wireless conductivity sensor is conductivity, but I could display another of its measurements by selecting the measurement name here and choosing an alternative. Notice that this same menu offers the chance to calibrate the sensor. I'll leave the live data page displaying conductivity in microsiemens per centimeter. As its name implies, the live data page is showing live readings from the sensor, which becomes clearer once I put the sensor in the beaker of distilled water. The live reading from this page of Chemvue may be sufficient for a chemistry investigation that requires only measurement monitoring. But 3 additional pages provide different data displays and the ability to record data to visualize changes over time. The table page offers columns of time and conductivity. The graph page shows conductivity on the y-axis and time on the x-axis. Finally, the graph and table page combines those 2 displays together. I'll focus on this page to investigate the changes in conductivity when I dissolve equal amounts of different types of salt in distilled water. While the live data page continuously monitored the connected sensor's measurements, Chemvue's other pages provide a record button that puts you in control of data collection. With the conductivity sensor in the first beaker of distilled water, I'll press record to begin collecting data. Notice that each time and conductivity measurement in the table is represented in the graph by a dot. The conductivity of distilled water is very low, nearly 0 microsiemens per centimeter. I'll add 0.01 moles of sodium chloride to the water and let that dissolve to reach a final conductivity. While we wait for that, notice that the table automatically scrolls to keep the most recent measurement in view, and the graph automatically scales both axes to ensure that all data is visible. However, we do have manual control over the scaling of the graph. Click anywhere in the middle of the graph and drag to pan the graph left, right, up, and down to change your view. Click and drag the numbers on either graph axis to compress or stretch the axis scaling. To quickly return to the data filling the graph space, press the Scale to Fit button, one of many graph tools. We'll explore more of these graph tools shortly. Based on the leveled off graph, it appears that the conductivity has become fairly stable, which I can confirm by looking at the latest values in the table. So I'll press Stop to end data collection. All of the data points collected between my pressing Record and Stop comprise a run of data, which we can see in the graph legend is called Run 1. We can manage the runs in a Chemvue file here. Manage Runs lets me delete a run, change its color, and rename the run. I'll change the name of Run 1 to include the solute I added, sodium chloride. Back on the graph, I can also label specific data points within a run by adding a note with this graph tool. I'd like to note the addition of sodium chloride and the quantity. The note is attached to a data point somewhere in the middle of the run by default. I can change the point it identifies by dragging the gray box and dropping it near a different data point. I'll fine-tune that by clicking on the label and nudging it point to point. I can also independently position the label and edit its text. Next, I want to determine the conductivity values both before the sodium chloride was added and after it fully dissolved. The graph's coordinates tool can help with this. The coordinates tool looks a lot like the earlier note, but it automatically labels the x and y coordinates of its data point. I'll move it to a point before the salt was added. I can add a second coordinates tool to a data point near the end of the run. And I could determine the difference in conductivity by doing the math myself with the values from these two coordinates tools. But Chemvue offers another tool specifically for determining the changes between data points. The delta tool, delta for change, is hidden in the label of the coordinates tool. Turn on the delta tool to provide a second handle that can be dragged to a different data point. The delta tool displays the change in x and change in y between the two data points. In this case, the initial conductivity was so close to 0 that I'll just rely on the conductivity reported by the second coordinates tool and remove the first one with its delta tool. I'll rinse the conductivity sensor in preparation for collecting a second run of data with calcium chloride. Starting with the sensor in a new 100 milliliters of distilled water, I'll press record to begin data collection again. And I'll add 0.01 moles of calcium chloride this time. Notice that run number 1 disappeared from the graph as soon as I began recording run 2. This is Chemvue's default graph behavior, designed to minimize clutter. In this activity, though, I think it might be instructive to view both runs at the same time while waiting for the calcium chloride to dissolve. In the graph legend, the checkbox to the left of the run name indicates whether the run is visible or hidden. I'll make run 1 visible again by checking its box. Now that the conductivity has stabilized, I'll press stop to end run 2. I can rename the run to include calcium chloride. And I'll hide run 1 again before continuing to analyze run 2. I'll also add a note on run 2 to indicate the addition of calcium chloride. To determine the final conductivity, I could use the coordinates tool again, but instead I'll introduce a new graph analysis tool, statistics. From the statistics button, I'll choose to show the maximum conductivity value of this run, which is displayed here, both its value and its location along the y-axis. Making run 1 visible again, we can see the difference between their fully dissolved conductivities. But is that difference meaningful? To help determine that, I'd like to show the error bars for the measurements from the wireless conductivity sensor. From the Graph Properties button, I'll open Error Bars and choose to show error bars. If I were to follow this link to the sensor's product web page, I'd learn that the accuracy of the wireless conductivity sensor is plus or minus 5% over most of its range. So I'll select percent of value for the error bar type and enter 5 for the percent error above and percent error below. With the error bars displayed, it appears to be valid to conclude there is a significant difference in the final conductivities between dissolving the same number of moles of sodium chloride and calcium chloride. Why are they different? Well, the ratio of these conductivities is about 1.5. That's 3:2 comparing calcium chloride to sodium chloride. And 3:2 is the ratio of ions produced by dissolving calcium chloride, CaCl2, compared to sodium chloride, NaCl. So, the conductivity measurements appear to provide insight into how these two substances dissolve in water. What would you predict to be the final conductivity for dissolving 0.01 moles of aluminum chloride, AlCl3? Find out for yourself by recording a third run. Although it's not the focus of this investigation, in some experiments, you'll be interested in determining rates of change. With this existing data, we might ask, what are the rates of conductivity change for the initial dissolving of each substance? A linear fit, one of many available curve fits, reports its slope, m. It starts out by fitting the entire run. However, I can restrict the curve fits analysis to a smaller range of data points within the run. First, I'll enable data range selection. Then, I'll click and drag a box on the graph to include the data points I want to analyze. Notice that the data points within the selection are highlighted yellow, and the curve fit dynamically adjusts to analyze only those points. I can adjust the size and location of the selection box after I've drawn it. So I see that the initial rate of change in conductivity for the calcium chloride was 1,160, and that's microsiemens per centimeter per second. Why did Chemvue choose to apply the fit and the selection to run 2 and not run 1? Well, that's because run 2 was the active run when I turned on those tools. The active run is indicated by a box around its run symbol in the graph legend. To analyze run 1, I'll first need to make it the active run by clicking on its symbol in the graph legend. Now I can turn on the linear fit for run 1 and adjust it using a selection. To determine the initial rate of change of conductivity for sodium chloride. Before continuing, I'll simplify my graph again by removing these selections and the linear fits. So, I've returned to just a view of the analyses of the final conductivities. Once you've collected and analyzed data in Chemvue, how can you save and share your findings? Here are 3 options. The most fundamental approach is to preserve everything about the file, including data and analyses, as a native Chemvue file. From the main menu, I'll choose Save and give the Chemvue file a name. Notice that Chemvue files have the extension .chemlab. These files can be opened by Chemvue across all of its supported computing platforms. If I wanted to bring just my recorded sensor data into another application, I could export that data from Chemvue. Returning to the main menu, I'll select Export Data. This creates a CSV, or comma-separated value file, that can be opened in a spreadsheet or other data analysis application. Keep in mind, though, that this file contains only the collected data, but none of the displays or analyses. Finally, If I want to share just a picture of my displays and analyses, I can export an image of the current page with this button. This creates a PNG image file, compatible with just about any application that handles images. For example, I could bring this image into a word processor document to start my lab report. Keep in mind, though, that this PNG is just a static snapshot of Chemvue's dynamic displays. I hope this tutorial has equipped you with the tools and confidence to use Chemvue in your chemistry investigations. We've covered some of the core features of Chemvue's general data collection module, appropriate for most Pasco sensors used in chemistry. If you instead connect specific Pasco instrumentation, like a spectrometer or a melting point apparatus, Chemvue will offer a different module tailored to the needs of that data collection device. Please visit Chemvue's product page at pasco.com for additional videos, licensing information, Chemvue help, and student-ready experiments. Happy experimenting!